A very good day and Assalamualaikum to distinguished professors, fellow colleagues, scientists, engineers, students, academics, ladies and gentlemen. I am Dr. Shahrom Mahmud from School of Physics, Universiti Sains Malaysia, together with my colleagues Dr. Motarasu Devarajan and Dr. Muna Repa. We express our deepest gratitude to the organizers of TESA 2020 for honoring us with this keynote speech. We are from the Thermal Management Research Lab, the lab devoted to solving thermal management problems in electronic devices, including LEDs. And today we will share our work on the impact of thermal interface material and substrate on luminous flux curve of indium gallium aluminum phosphide low power LEDs. The outline of our speech involved the abstract, in which we discuss the research gap of thermal management issues of commercial low power LED, and we will present an overview of what we have done in this particular work. The principle involves the heat transfer theory that we use to explain the thermal resistance with the employment of thermal interface material. The methodology, we will explain how we prepare the samples and how we characterize them. Results focus on thermal resistance, junction temperature, electrical power and luminous flux. And finally the conclusion. Abstract. For this work, we focus on commercial low power LED, which are used a lot in the automotive industry, especially in the signal lighting and the interior of the car. From the figure there, we can see the LED chip, the white square, from which luminous light emanates and from which heat is generated. The LED package is designed to provide conduction path for heat to dissipate to the heat sink. Item 1. The heat dissipation behavior affects the light output of the LED, its reliability and lifespan. Item 2. The LED junction temperature, okay, for this low power model is very much affected by the ambient temperature rather than the input current. Number 3. It is known that 70 to 80% of the electrical power supplied to the LED is wasted in the form of heat, and this is our motivation in our effort to bring down that percentage. The schematic diagram shows a cross section of the LED package. Item 1 is the LED chip that generates heat that must be removed from the package. The chip is connected to the metallic lead frame. Since it is metallic, it has high thermal conductivity that offers good conduction path for heat to flow all the way down to the substrate and heat sink. Item 2 is the molding compound, which is a dielectric that offers physical integrity to the package. Item 3 is the area of concern of this work. It is a void space or air gap, and we find that many customers of low power LED, they do nothing to this void space, and we found that this void space is the culprit that acts as a thermal barrier against heat dissipation from the molding compound to the substrate, resulting in higher thermal resistance and lower luminous flux. What we did, we fill up this void with thermal conductive material that increase the surface contact area that promotes heat dissipation from the molding compound to the substrate, resulting in higher performance of the LED. Another project that we did was we worked on different material of the substrate. Item number 4, we worked on metallic aluminum and epoxy glass, in which aluminum substrate perform better. For the principle, it is known that lower thermal resistance or RTH offers better thermal management or cooler LED. Item 1 shows the conventional model for low power LED. In this particular package, there's no TCM material. There are voids in this package, and the total thermal resistance are the summation of the thermal resistance of the LED, solder, and substrate. For our case, we fill up the voids with thermal conductive material or TCM material to form a layer which is parallel to the solder. So that is shown in item 3, where the RTH of the TCM layer and solder layer are parallel, and the value of the parallel arrangement is shown in equation 4, which will give a much lower RTH for this parallel arrangement, and the summation of all the RTH will give a total resistance which is much lower than the one in the conventional model. Methodology: we purchased commercial low power indium gallium aluminum phosphide surface mount LED as shown in the photograph in item 2. That is the actual sample. The LED produces luminous light at the wavelength of 317 nanometer. That corresponds to the amber color, which is used in automotive lighting as in item 4. The item 3 shows the basic structure of the LED package. The table on the left compiles the specification of the low power LED, and focus is given on the lower part of the table, which is the substrate thermal conductivity values. FR4 is the epoxy glass at low value at just 1 watt per meter Kelvin. The aluminum based substrate has 200 times more in terms of the thermal conductivity, and we will see which one is better in terms of the heat dissipation response. We worked on 2 parameters. First was the thermal inactive material or TIM. The other one is the substrate study. For item 1, TIM material, we used thermal conductive epoxy or TCE and thermal conductive adhesive TCA, referring to the image of the cross section of the LED. Item 2 shows the void, which is the focus of concern in this work. We fill up this void with TIM material, TCE and TCA. That is shown in item 3, the cross shape area. That is the TIM layer. And we acknowledge the assistance from the industry who assisted us in this sample preparation. The other parameter is the substrate study. We use a couple of material, the epoxy glass or FR4 on the left, and the metallic aluminum base on the right. Since it is metallic, we need to apply the dielectric layer to offer electrical isolation. In our lab, we have T-tester and parallel system as shown in the photograph of item 2. We use this system to measure the optical and thermal properties of the LED packages. Item 3 shows the schematic diagram of the measuring system. The location of the mounting of the LED package is shown there. We pass current from 50 mA to 300 mA at ambient temperature. The higher the current, the more light the LED produced, and the light is captured by a detector linked to the black dome as shown in the photograph. At the same time, the cooling transient curve was recorded by the T-tester equipment. There is a software that processes the data to a form that we can use. Since we are dealing with commercial LED, we perform measurement according to the specification prescribed by the International Commission on Illumination or the CIE specs. For results, we start with the substrate study. The figure on the left shows the structure function curves, K factor versus RTH. K factor is described by the equation in item 1. Item 2 describes the RTH property. The structure function curves are very important because they are used to determine the thermal resistance of LED packages, and it is determined from the 0 point, the item 3, from 0 point to the onset of the curves. For example, the black curve corresponds to the IR4, the epoxy glass substrate sample. The onset occurs at about 95 Kelvin per watt of the RTH, whereas the other sample which use aluminum metallic substrate, the blue and red curves, has RTH value or the onset at around 66 and 60. So this shows that the RTH value of the metallic or aluminum based substrate has better heat dissipation response if compared to that of the epoxy FR4 substrate. In item 5, the luminous flux versus input power response is illustrated. The blue curves shows the best response in terms of luminous flux, and that blue curve belongs to the aluminum metallic substrate with the 5 watt model, and the maximum lumens is about 36 lumens at 0.6 watt power, compared to the lowest value for the luminous flux, which is the black curve that belongs to the epoxy glass FR4 sample. The lumens is just around 24 lumens. So this proves that a lower RTH or lower thermal resistance has the benefit of producing higher luminous flux of the LED package. Therefore, it is advisable that aluminum or metallic based substrate is a better choice compared to the epoxy glass substrate in terms of performance. An interesting observation is that the manufacturer of the LED specified a low rated power of only 0.1855 watt that produce a luminous flux of only 15 to 15 lumen, which is quite low. In this work, we increased the input power all the way to 0.9 watt, and we discovered that the maximum possible attainable luminous flux is around 36 lumens at 0.6 watt. So why manufacturer of LED give such a low rated power for their product? There are a couple of reasons. First, there is a thing called the factor of safety. So company tend to declare a performance which is less than what the product can offer. This is has the advantage of lengthening the LED lifetime, and the second reason is to improve the luminous efficacy. So from these results, we can see that the LED package performance can be determined by the choice of the substrate. If you choose a metallic based substrate, then you can have a much lower thermal resistance, which have the benefit of producing a much higher luminous flux. The results from previous slides can be compiled in this table. The best performance are shown by the aluminum 5 watt metal core PCB sample, whereby we have the lowest thermal resistance of RTH of just 60.97 Kelvin per watt, that produce a drop of junction temperature of just 1 degrees. That is followed by the highest luminous flux of 36 lumens. So even though the drop in the junction temperature of only 1 degrees, that is enough to show very big benefit in terms of the luminous flux, and this response is supported by the photoelectrothermal or PET theory that suggests The maximum luminous flux depends on the cooling effectiveness. Cooled by just 1 degree is sufficient to give huge impact on the luminous flux. Item 5 shows the equations which are used to determine the luminous flux and the electrical power in this particular study. We discuss the results for the thermal interface material or TIM study. Here is the infrared thermal imaging results. The samples on the left column are the ones without TIM material, which means they contain voids that acted as a thermal barrier that hinders heat transfer. Therefore, these samples tend to experience heat accumulation that result in higher temperature that is shown in the item 1 and 2. Not only that, you can also see there is heat accumulation at one side. The samples in the middle and right columns are the ones that contain TIM material that fill up the voids with epoxy TCE and adhesive TCA that produce huge surface contact area for much better heat conduction and better heat dissipation, resulting in better heat spreading. The outcome is that the sample exhibit lower temperature in the infrared thermal imaging, especially the item 1, the temperature drops from 66 Celsius to 61 Celsius, which is almost a 5-degree drop in temperature with the TIM material filling up the voids. Comparing the two types of TIM material, epoxy TCE versus adhesive TCA, the adhesive TCA perform slightly better than the epoxy TCA since it has better surface adherence that produce more surface contact area for higher and more effective heat conduction. These are the thermal resistance and luminous flux results from the TerraLab system. The figure 1 and 2 are the results that compares the thermal resistance performance between the two types of TIM material, TCE epoxy versus adhesive TCA. The figure 3 and 4 are the luminous flux data that compares the performance of the epoxy substrate and the metallic aluminum substrate. Due to the complexity of the data, we compile the results in a table which is presented in the next slide. This table summarizes the results from the data in the previous slide. Item 1 shows improvement in the thermal resistance by an extra 30% by filling up the voids with TIM material, and there is improvement in the reduction of the junction temperature by 2 degrees, which is have the benefit of giving an extra 30% in the maximum luminous flux up to 32.7 lumens. The same response is observed in the metallic substrate in 3 and 4. The improvement in thermal resistance is about 20%. The same goes for the luminous flux, which deliver a luminance of 36.6. Coming to this stage, we now realize the huge impact of thermal interface layer in commercial low power LED, whereby this TIM layer reduces thermal resistance and the junction temperature, resulting in a more efficient LED and brighter LED. The best results are obtained from the TIM material that use the adhesive TCA, whereby we get the lowest thermal resistance, lowest junction temperature, highest power and highest luminous flux. And this can be explained by the fact that the adhesive TCA offer bigger surface adherence than the TCE, thereby bigger contact area, resulting in increasing the cooling effect of the substrate. There are 4 conclusions for this work. The first one, filling up the voids in low power surface mount LED with thermal interface materials can increase surface contact area that promotes effective heat conduction for superior heat dissipation, leading to lower junction temperature and higher luminous flux of the LED. Secondly, adhesive type thermal interface materials offer better surface adherence than the ones in epoxy types due to their bigger surface contact area. For the third conclusion, thermal interface materials promotes good heat spreading, thereby removing LED overheating problem and high junction temperature. Finally, the last conclusion, number 4, with better LED packaging design, TIM and substrate, the performance of commercial low power surface mount LEDs can be improved for higher luminous flux and electrical power, which means that less LED units will be required to achieve the desired output. We feel very honored to share our research finding in this prestigious TESA 2020 conference, and we thank you very much for your kind attention.